this semester, I've specified an instruction set architecture and designed and implemented a conforming microarchitecture. I'm going to call the architecture the CSCI-E-93. My microarchitecture implementation I will be calling joules. The ISA specifies a 2 to the 16 or 64 kilobyte address space, which is byte addressable. The only way to modify memory is to use the load and store instructions. I've specified both word, 16-bit, and byte, 8-bit, variants of both of these instructions. There are a total of 28 instructions. We will see some of them in more detail later, including a hardware multiply instruction which I implemented for the final project. Another important part of the architectural state are the 16-bit general purpose registers, along with a specified application binary interface convention. The CSCI-E-93 ISA general purpose registers are displayed in the table. When using the provided assembler, users may refer to these registers by their canonical names listed below. For example, $x0, $x1, $x2. Additionally, every register has an alias corresponding to the usage in the architecture's prescribed ABI convention. Register X0, or the 0 register, will always return the value 0, and writes to this register are discarded. Register X1, or RA, holds the return address when in a called function. It is the implicit target of the jump and link instruction. Register X2, or alias SP, conventionally points to the top of a descending stack. This means that the stack grows toward lower memory addresses and that the value in register SP is the address of a valid word in the stack. It is not an empty descending stack. It is the programmer's responsibility to set this value early. Registers X10, 11, 10, 11, 3, and 4 conventionally hold the first 4 arguments when calling a function or subroutine. Additional arguments must be passed on the stack. A calling function should not expect the contents of these registers to remain unchanged after a callee function returns. In fact, these same registers are used to return values from functions or subroutines. So the register A0 is both the register that holds the first argument when calling a function and the register that holds the first return address when returning from that function. I save 5 more registers for temporary registers, X5, X6, X7, X14, and 15. A calling function should not rely on the contents of these registers to remain unchanged across a function call. And finally, the 4 remaining registers, X8, 9, 12, and 13, are called saved registers because a calling function can expect the contents of these registers to remain unchanged across a function call. A callee function must save and later restore any S registers it changes during its execution. Talk briefly about the instruction set. So I only had 16 bits of encoding space to work with, and so I implemented 4 different types of instructions. A register type that takes 2 registers and writes to the first one, the result to the first one. I have a register immediate that takes a register and a 4-bit immediate value and writes back. These are for the shift and shift immediate instructions. I have instructions that are immediate instructions where 8 bits represent an immediate. I also include branch instructions, and these have an encoded 8-bit immediate that is shifted left because we are branching only to instructions, and so they have to be word aligned. We also have store and store byte, load byte, and our jump instructions. Anyone wishing to program against the CSCI-E-93 ISA and to program the Joules computer can use the provided assembler. This assembler accepts a single .s file containing assembly code and produces a single .mif file, memory initialization file, that can be later loaded into memory. The assembler supports pseudo instructions, directives, comments, and labels. This is an example program that we will later run. It takes two 16-bit signed numbers and multiplies them together and outputs to the console. Notice that we have comments, labels, we have directives for words, and also directives for text. And we can run the assembler, and it will produce a MIF file. Notice that some of the pseudo instructions get expanded into two actual instructions. The assembler retains comments as well as the original instruction for ease of debugging. In order to be able to allow us to more quickly test our software and detect bugs in our microarchitecture or software, we implemented an emulator to model the ISA and run CSCI-E-93 assembly language programs. After creating the MIF file with the assembler, we can use the emulator to run with the MIF file. The emulator has a default mode of no step through. So this is the program that multiplies two numbers. It goes in a loop forever. The emulator can also run with a debug flag where we can step through and see every stop before every instruction, and it also shows the contents of all of the general purpose registers and highlights any changes from the previous instruction. So I'm going to run the program for a little bit. It pauses to take input. Also, we can use the M command to move into a memory viewer mode. You can scroll with the up and down arrows through memory. You can also use the colon and write a 4-digit hex value to move to very close to that location in memory. So our stack is in DD00, I believe. Yep, right here. And so we see some values on our stack. And we can go back to 0000. And this is where all of our instructions live. And we can exit the memory mode with :Q and continue stepping through the emulator. The DE2-115 can be programmed via the Quartus software toolchain provided by Intel. For my final project, I completed a VHDL entity to program the DE2-115 as a conforming microarchitecture of the CSCI-E-93 ISA. Additionally, I implemented a hardware multiplication unit where computations complete in logarithmic time, log base 2n, where n is the number of bits, in my case 16. After implementing this hardware, I amended the ISA specification to include a mult-u instruction. On the left is a subroutine, is an assembly language program that multiplies two signed numbers in software using the shift and add routine. On the right is the program that uses the mult-u instruction. Since both of these programs still need to multiply two signed numbers, and the hardware instruction is unsigned, there is some software to keep track of the sign and to negate the results accordingly. I'm going to program the FPGA. I want to briefly show the DE2-115. If I press this will reset the memory. I can push this up so that I can step through. I implemented a few debugging features. This controls a mux to output debugging content. So in this position, I can toggle these as an index into my register array. So I currently have, according to the bit number index, that's the content of the register on reset, just so I can debug. Value 2 here shows me my instruction, my current instruction. So if I let the clock hold down, this is my instruction. I can see the PC value with that, and I can see the immediate value if one's relevant. These two displays were useful for clock stepping through my memory protocol. So that is an input to the memory subsystem and an output from the memory subsystem. And I can step through the different states. So I'm reading an instruction right now in state 4. So I'm waiting for this to go low, and now it moves to step 5 and step 6. And now we're actually executing the instruction, which is this instruction C.
And if I remember correctly, that C means we are jumping right now. So that's it.
This is a time test of the multiply software version. Multiply -400 with 4, and I'm going to try to hit enter and the stopwatch at the same time. We'll see if this works. And that is 3.91 seconds. Now we're going to come back over here and load the hardware version. And we're going to reset. So -400. Let's reset this. 4. Didn't do it. Let's do it again. -400. 4. And there's 2.74 seconds. So very crude test. If I had more time, I think I would implement a non-architectural register to count the number of cycles between 2 points of a program. But this timing shows that the hardware multiply is, from my testing, around 20 to 25% faster. I'd like to take a small bit of time to say thank you to Professor Jamie and TAs. Thank you, Mark. Thank you, Stephen. And thanks for the time. This was a great class. And also thank you to all my classmates as well. So let me know if you have any questions.